Okay, let's take a look at question 6 from exercise 1.3a. The roots of the equation z minus 2 divided by z plus 3 divided by z squared plus 2 divided by z cubed plus 2 equals 0 are alpha, beta, gamma, and delta. Using a suitable substitution, find the equation that has roots 2 alpha, 2 beta, 2 gamma, and 2 delta. No problem. So if you want to make this into a polynomial, you can times everything by z cubed. So we get z to the power of 4 plus 2z cubed. And then the other ones, minus 2z squared. And then plus 3z. And the last term is plus 2. Right, so that equals 0. So that's our equation p of z equals 0. And our function f, which takes the roots alpha, beta, gamma, and delta to 2 alpha, 2 beta, 2 gamma, and 2 delta, is f of z equals 2z. Okay, and then we know that's p of f inverse of z equals 0 has the roots 2 alpha, 2 beta, 2 delta, and 2 gamma. And clearly f inverse of z is 1/2 z. Alright, so we just put 1/2 z into there. So we got 1/2 z to the power of 4 plus 2 times 1/2 z cubed minus 2 times 1/2 z squared plus 3 times 1/2 z plus 2 equals 0. And then from there we can just simplify it. So 1 over 16 z to the 4 plus 2 over 8 z cubed minus 2 over 4 z squared, and then plus 3 over 2 z, and then plus 2 equals 0. And then as the last step, just times everything by 16 to get integers. So z to the power of 4 plus 2 times 16 divided by 8, so 2 times 2, so that's 4, so 4z cubed, and then 16 divided by 4 is 4, so minus 2 times 4, so minus 8z squared, and then plus 3 times 8, so 24z, and then plus 2 times 16 is 32, and then that should equal 0. So that is a quartic equation that has those 4 roots there. Okay, and while we're here, let's take a look at question 7 as well. Sophia would like to find a quartic equation where 2 of the roots are 2 minus I and 3 plus 2i. Rafaela says the other 2 roots must be negative 2 minus I and negative 3 plus 2i. Well, if the coefficients of the quartic equation are real numbers, then, well, for part A it says explain the mistake that Rafaela has made and write down the correct other 2 roots. So Rafaela has made a mistake about what complex conjugates are, and so the other 2 roots must be 2 plus I and 3 minus 2i. So those are the correct other 2 roots. So Rafaela's mistake is that he doesn't know what complex conjugates are. And then for part B, it says find a quartic equation with Sophia's roots. No problem. So for part B, well, I guess the quickest way would just be to write it as per the fundamental theorem of algebra allows us to in the product of linear factors form. So z minus 2 minus I times z minus 2 plus I times, and then the other two, z minus 3 plus 2i, and then z minus 3 minus 2i. And since the roots are complex conjugates of each other, the imaginary components are going to cancel out, and we're just going to be left with real coefficients when it gets expanded. So let's go ahead and do that. So just expanding this pair of brackets, so we get z squared, and then minus 2z, and then minus 2z again, so that's going to be minus 4z, and then as we said, it's going to be minus negative I times z, and then just minus positive I times z. So those parts are going to cancel out, and then so the rest of it is just going to be minus 2 minus I squared. So, sorry, minus 2 minus I times 2 plus I. So plus 2 minus I times 2 plus I. And that's really quick to calculate as well, because it's just 2 times 2 is 4, and then minus I times positive I is 1. So the whole thing just becomes 5. So plus 5. And we can do the same for the other pair. So z times z is z squared, and it's going to be minus 3 times z and minus 3 times z. So that would be minus 6z. The I components cancel out for that middle term. And then the last part is just minus 3 plus 2i times minus 3 minus 2i. So again, that's just going to be 3 times 3 is 9 plus 2 times 2, so plus 4. So that will be 13. By the way, this should equal 0 since it's a quartic equation. And now what we got to do is expand it out by multiplying everything by everything else. So that will be, so just taking the z squared and multiplying it by the 3 terms, so that will be z to the power of 4, and then minus 6z cubed plus 13z squared, and then the minus 4z, so that will be minus 4z cubed plus 24z squared, and then minus 4z times 13. 4 times 12 is 48, so that would be 52, so minus 52z. And then lastly, plus 5z squared minus 30z, and then plus 65. And this whole thing should equal 0. And now all we got to do is just add it up. And we get z to the power of 4 minus 10z cubed, and then 29z squared plus 13z squared, so 42z squared minus 82z plus 65, and that should equal 0. So that's our quartic equation down there, and it should have the roots 2 plus I, 2 minus I, 3 plus 2i, and 3 minus 2i.